All right. Hey, Alex, how are you?
Good, how are you?
I'm doing great. Did you have a good fourth?
Yeah, how about you?
It was wonderful. That weather
Good.
was amazing, wasn't it? Hot, but it should be on the fourth. Let's see here. I'm pulling up some old exams. Or I'm just gonna pull. Actually, I might just do the one from last year. Let's see here. Tests. Here we go. Yeah, I think I'm gonna do test solution spring. Yeah, there we go. All right, so I'm going to go ahead and just, first of all, I'm going to just talk through the formula sheet a little bit. If you haven't been deeply involved using it, it's still okay, but I just want to show kind of the role it plays or can play. I just got done grading somebody's exam, and they did a marvelous job of kind of using it appropriately, I thought. Maybe even probably more than they needed to, let's put it that way. So do you all see that on your screen? The formula sheet.
Yes.
So do you know how to resize it? In the upper left-hand corner, there's a little um, zoom button thing there, view controls, and you can make it a little bigger so you can see it easier. Anybody okay with that?
Yep.
Okay, thanks for the chat there, Heidi. All right. So pretty much, I made this formula sheet to make it, well, hopefully as easy as possible. It's never that easy, but it's just two sides. One side is all confidence intervals. That's page one, and the sample size formulas. And then page two is all the ones for hypothesis testing. So the first question, if you're trying to figure out which one to write down on your exam, I suggest this in the directions of the exam, that if you just write down the correct formula, even if you're using StatCrunch or whatever, I can still give you partial credit because you're like, oh, I understood that was a one proportion z-test kind of thing, or that was a two proportion or one mean or two means or dependent. That helps me know you know what we're talking about based on the context. And that's one of the harder things, even with StatCrunch, is you have to know what's being asked. So the three questions you want to ask yourself are, is it a hypothesis test or a confidence interval? That gets you half of them, right? Splits it in half. The next question, really for our examples, I don't do a ton on deviations on your exam. There's an extra credit question at most that studies the confidence interval for variance, and I think it's on this exam here. But pretty much all you're going to ask yourself, are we talking about means or proportions? So if it's proportions, you're going to be using Z, and if you're using means, we're going to be using T. So if it's confidence interval or hypothesis test. And then the last question you really have to ask yourself, is it one sample, two samples, or it could be paired data, this very last one that you did in the last section. So you can look, and pretty much based on the sample data you're given, you'll know. So if I give you one sample with a mean and standard deviation, you know it's just going to be one sample mean, like this T here. Can you all see that pointer? I'll get my pointer there. How about that one? So that'd be one sample mean. Use that one. There's two sample means, one proportion, two proportions, and I think I'm on the exam. I think I'm pretty explicit. This unpooled method is they're almost going to be identical. This pooled method helps if there's a large disparity between the two. It helps even it out, but honestly, it's going to be this unpooled, and you'll see that on the test that's even written that we're going to go over right now. But I just put that in there because there's a few homework problems that talk about that. And then if it's one proportion, same thing on the other side. If it's confidence interval, confidence for one proportion, two proportions, one mean, two means, and paired data. Paired data, remember, is just it's either the same person being tested twice, or the very associated or dependent data. Like, for instance, my age and the age of my wife, that's paired data. They have an association between the two. Um, Weight loss, I weigh myself, do this thing, and then I weigh myself again. That's the same person being tested twice. That's what the the last section, I think section 9.5 was about. And you'd be given the sample mean and sample standard deviation on these. So as far as the formula sheet is concerned, is that, I think I had a video on Blackboard already in this, but I don't know how questions over and above just how to navigate picking one, because just picking one will get you a lot of credit on your test, picking the correct one, obviously. If you use StatCrunch and you don't write this down, but you're correct, I'm not going to count you off, but I can give you some partial credit if you're, picking the right type of scenario. And you don't even have to put the numbers in. You can just write the formula down. That's fine. How does that sound? So this, like I said, is that okay? Go ahead.
So the one that I had emailed you about, I think it was letter F on one of them.
Yes.
On a practice exam. I don't know what I was doing. I couldn't figure out how to find a formula for that, or like how to plug in the right numbers, but I knew how to do it on StatCrunch. So is that going
totally
to
fine. Yep.
lose me points or no?
Nope, won't use anything. So for instance, like on this one, let's say you just did this, a one sample z-test for proportions, and you didn't do any of this work here. You just wrote this formula down and you had this answer. That's fine.
Okay, thank you for the clarification.
And if you have the correct answer here and here, and you don't have this, you're still getting full credit.
Okay.
So
if it doesn't specifically, if it doesn't specifically ask for the correct formula, we don't need to put it for full credit, or we should?
Right, I'm telling you, the new instructions I made on the new exam I wrote just says, if you want partial credit, if you miss it, put the formula down.
Gotcha, perfect, thank you.
Does that seem fair?
Yeah, works for me.
I mean, because otherwise, if I just sit there and somebody writes down a z-score that's bizarre, and it might be just because they mistyped something, or they didn't divide right, or they didn't put the square root over this whole, there's a million ways to make a little calculation here, or click the wrong button, right? I hate to take off all those points, but if they could show me that they know this is a z-test for one proportion, that's actually the most important part. So I want to give them some credit. So, and for instance, let's say you make a mistake and it causes you to have the incorrect p-value, but you make the correct decision based off that incorrect p-value. I'm only going to take one off. I'm not going to kill you on both of these. So I try to do my best to see what your line of thinking was. Did you? Oh darn! You made an error on the z-score, or on the z-score, which made an error on the p-value, which made you make the wrong decision. I will still probably only take one off for that. Because if you follow the line of thinking that you had based on what you did. So I don't just smoke you and say, oh, you missed all 5 of those points. Not going to do that. So that's why I'm just encouraging everybody to kind of write it out. The one error I see a lot is, it says state your conclusion and explain in the context. So a lot of people say, since P is greater than 0.05, failed to reject. Okay, now you have to explain it in context. There is not significant evidence to say the employer discriminates or something like that. You have to refer to the problem situation in your explanation. So if we reject, there is significant evidence. If we fail to reject, there's not significant evidence. Pretty much, I think you got that pretty clear from all your online homework as well. And then same thing with type 1 and type 2 errors. Type 1 is when we reject the null and we were incorrect. So reference the context. Reject the null and say the company did discriminate, but they really didn't. Failed to reject and say they did not discriminate, but they really did. Something around why, this particular problem, this context. So just be kind of cognizant to tie it back into what you're actually analyzing here. Questions on that? Have you guys all seen this test already and went through it yet? This is from last year. And there's like 5 old ones out there. So if I really wanted review for this exam, I would just there's a clean copy of this exam. You could either look at it on your screen and write out your answers. If you want to print it, you can. Doesn't matter. And just practice taking it. There's a 2-hour time limit. Okay, cool. Yep. And then you can just watch the solutions video, go through them, see if it makes sense. If there's something you're not sure about, like Alex said, that's great. Then shoot me an email and say, how'd you get this? Or would it be okay if I did this? And typically, if students have done all the homework, have gone through these kind of basic review things, gone through a few old exams, there should be very good test scores. The ones I see that don't are the ones who did almost none of those things. And I can't help much at that point, but well, the fact that you're all here is a good sign, and people will watch this review hopefully and pick up a few tips. So as far as this first page, any questions? I'll go to the second one if that's all right. But does it seem there's a few people in the chat here? Okay, cool. Yes. Yep. Because the thing here about statistics is, yes, there are some computational things we do, but I'm more interested in statistical thinking and how do we communicate that statistical thinking properly. And that's really what we're trying to get you to practice and think about here. And also be just critical analyzers of results you get, and how far can you actually say based on the question and how the sample was gathered, and what biases, what errors, what lurking variables. There's a lot of things to think about, but for a first statistics course, I think we get you pretty far down that path of how to think this way. So if you, like, I know we have somebody in this class who's going to take a graduate level statistics class this fall. And I've had many students take this course to prepare them for a graduate level stats course. And it does a pretty good job of getting you ready for that. Because the statistical thinking, I don't care what test you end up doing, you're still going to end up with this thing called a p-value. And the p-value is just describing the probability of getting that result by random chance. So if we observe something that is very rare or almost unexplainable by random chance, we start to think something's going on here. Something else is making this happen, which you all did in your discussion boards. The joke is I've stopped letting my kids say something was lucky or unlucky. I make them say, well, you've just observed a rare event. Rare events happen, and we observe them sometimes. Is it a low probability of happening? Probably, but that doesn't mean it's not explainable of why it actually happened. They don't like me very much sometimes when I talk to them like that, but it helps them think statistically as they're walking around my house. Or even if they're playing a video game and something, they'll say, oh, you got lucky. I'm like, no, it's probably completely explainable by physics or game mechanics. It just was a rare event that you observed, and they don't want to play games with me anymore either. So yeah, so I'll keep going on that. All right, so this one is with means. Remember to use the proper notation here. Mu for means and P for population proportions. Again, these are parameters that we're analyzing. So we're using statistics to describe samples. Parameters describe population. So we're trying to make an inference to a population based on a sample that we've analyzed. And so this was the average was 15 is less than 15. Calculate the t-score. P-value is greater than I guess we had a high threshold. This one was a 0.1, still higher than that. Usually it's 0.05 in every one of them. There's a movement in moving away from these hard and fast p-values, because p-values are determined usually before you begin any analysis. Because really a p-value is the probability of making a type 1 error. So think about this. I go and I do a study. I observe something. The probability of that observation happening by random chance is 3%. Now that could happen. You know, stuff happens. That's 3 out of 100. So for me to say that's statistically significant because it's less than 0.05, okay, The 0.05 is saying I'm cool with making type 1 errors 5% of the time. Now, sometimes that might be appropriate based on the context, like making the error may not be that big a deal, but well, there's certain things where it is a bigger deal. So this is why that alpha level is diverse based on the scenario. In this course, pretty much we just say 0.05, we give it to you, go do your thing. But I'd say in the quote unquote real world, you're going to be given p-values, and you're going to be the one that's going to have a sense if that's really statistically significant. When I see a p-value of 0.000001, the probability of that happening by random chance is like 1 out of 10,000. That's really strong evidence. If it's 0.11, like 88, and this one 12%, well, that could happen by random chance. But what this does is informs researchers: is there something going on here? Should we keep looking into this? Should we spend more time and money, get a larger sample, get a better sample? What other variables could be happening here? That's why it's always repeated. It's almost never a one-shot deal when people are doing research. But your ability to take if somebody says the p-value was 0.01, you're like, oh, okay, that's a 1% chance. That could happen, but that's maybe there's something going on here. Maybe there is a statistically significant difference in the population that we're now observing. That's the kind of thinking that we're trying to move you more and more towards, which I think when people do well in this exam and they explain their thinking well, they've done that. So there, I'm elaborating on why you're doing this more. So pretty much if the p-value is over the alpha, we fail to reject. There's not significant evidence that the average rod is less than 15 feet in this case. 95% confidence interval. This 2.131, you can find that right on your T table. I'll show you how to do that one. I'm going to go ahead and upload it, okay? Give me a second here. Let me upload that. You can use StatCrunch as well. You can use a StatCrunch T calculator, put in the degrees of freedom, put in the percentage between, and it'll give you the appropriate t-score multiplier there. Or you can just go right to StatCrunch with the raw data and say I've got to do a 95% confidence interval with summary, and away you go, which is assuming you've done it maybe in both ways. Let's see here, formulas, here we go. All right, so I'm going to pull this up now. So this has, there was what? Yeah, right here, degrees of freedom is 16 n minus 1. So there's 15 degrees of freedom. So I'm going to look in row 15, 95%. And I'm going to go ahead and share this now.
We can't see, we can just only see the exam still.
Yep, I got to click on it here.
Oh,
give me a sec. All right, now can you see it?
Yes, sorry.
Yep. Oh, no worries. I just had to click, I had to upload it. It took a little time. All right, so row 15, and you can see it's kind of a cheater down here. What confidence interval? That means 95. So it's this middle column, which is 2.5% in each tail, in one tail, or 5% between both tails. So there it is. The T multiplier is 2.131. And so that's pretty much, this is a way you can do it, or you can do it in StatCrunch, either one. If you look, if it's the z-score ones, notice as sample size increases, these keep getting smaller and smaller. In fact, as it goes to infinity, it becomes exactly the same as the normal distribution. 1.96 would be our z multiplier. Because notice, this looks like the normal distribution, but it's actually a family of curves. The lower the degrees of freedom, the more spread out, the more error we might find. As sample size increases, the more normal it becomes. This is actually called Gossett. It should be called Gossett's distribution. This dude came up with this. He wanted to figure out a way to analyze stuff without having a sample of a bajillion things. So he figured out, oh, if I do smaller samples, I can just assume a little more spread, and it still works. And he was right. And he actually worked for the Guinness Brewery. and they wouldn't let him publish this for many, many years. And he finally convinced them that this would actually help the world, not just me. But they said you could do it under a pen name, so he called this Students Tea Distribution. So that's how it got its name, and we've been using it a lot since then. So that was back in the, I think in the 1800s he figured this out. All right, so I'll go back to the exam. Okay, so, and then this is a one I did for extra credit, 95% confidence interval for the standard deviation. There's the formula. You get those chi-squared left and chi-squared right off your z-table or the chi-squared table. I removed this one on this exam, so there will not be a question on there like this time. So questions on page 2 or comments or? You guys still there, or am I droning and boring? I'm a college professor, I guess that's part of the deal, huh? Well, hopefully you're invested. This test is worth quite a bit. All right, we're good. All right, thanks, Alex. All right, so number 3, if you think about it, there's only really 5 types of problems. 1 sample proportion, 2 sample proportions, 1 mean, 2 means, and paired data. That's it. So really there's going to be pretty much 5 problems because that's all you can time allows, especially when you have this many parts. And sometimes I ask for type 1 and type 2 errors. Sometimes I ask for the confidence interval. Sometimes I don't. It just varies. And you'll look through the old exams how that varies as well. So this is a difference between 2 proportions. Notice we have 2 samples. We're just trying to find out, is there a difference in the rate of voting for Republican here? Yeah. So the null hypothesis is there's no difference. Alternative is that it's higher for men, I think. Calculate the z-score, 1.575. The piece value is 0.0571. You can use your z-table or the z-calculator. That is over 0.05, so we're going to fail to reject. There is not significant evidence that the proportion of men is higher for Republican than women. Is it look pretty close? Yes. Is there some evidence that it leans that way? Yes. So if this is a researcher, they might say, you know what, maybe we look a little harder. Maybe we sample 1,000 people this time and see if we can pull this out to see if the population reflects this or not, especially when it's this close. So this is one Iowa. We always have a lot of polls here, don't we? So this is a very relevant one when they're doing all that polling. A lot of people use election stuff for their final projects too. They'll look at you know, the national rate versus Iowa, or who voted for this president. I did had somebody do a really interesting one this last spring. This woman had a really good question. I think she was trying to analyze I think it was for Trump, was the proportion significantly higher than it should have been of white males. So it was interesting. I helped her a little bit. I tried to look it up. What percent of the electorate are white males? And I think it's 38%-ish, 34%, something like that, are white males. And I think we looked it up, and Trump got 36%, I think, something like that, of the white male vote, or something like that. And out of the 34, it should have been 34%. He got 36%. So it was a interesting. I think it was statistically significant difference, but I think she was surprised that it was only like a 2% off expected value kind of thing. So I don't know. It's kind of a cool project. A lot of people. I had a woman last semester did one on cancer rates in children because their child had cancer, and so she looked at like 20 years ago versus today and see if the rates have changed. And yeah, somebody did, I think, pay over time for certain occupations, and they did a linear regression on it, which you're going to be studying this week. You can do projects on that as well. There's a lot of cool ideas. So I'm excited for next week to see all of your discussion boards and interact with you about ideas you have for projects. And hopefully after this test, it kind of gets you thinking, what are some possible things in your major that you think would be a cool question to answer with existing data sets. So I've already had a few people message me as well with some really good ideas, so that's kind of neat. I'll just go through this number 4. Again, this is paired data. Like this is like a before and after they take this training, so it's the same people being tested twice paired. So that null hypothesis is mu sub d equals 1. If you're curious about the way these notations go, they're right on the formula sheet. I'll show you that. Go. The formula sheet, here we go. And if you go to the hypothesis test side, that's on page 2. So on this one, this is paired data right here. Notice, can you all see there's the null hypothesis and the alternative hypothesis? So this can give you some hints on proper notation. Yeah. So there they are right for you there to help you get the right notation based on the situation. Okay, go back to the test now. So number 4 here. So the null hypothesis, they're equal. The alternative is that it lowered, I think it lowered anxiety is what we're measuring here. And then we found the t-score to be negative 3.92, which is like a p-value of very small, like about 0.005 or less than 0.05, or if you use your t-table, it's just less than 0.05. If you use the t-calculator, I don't get too picky about how accurate you are in that. You're going to know it's definitely, since it's less than 0.05, you're going to reject it. Have significant evidence that training lowers anxiety. And then here's a 95% confidence interval for that. Again, we had the same number of degrees of freedom because it was 95% and the sample size was the same. So did make students look that one up twice, a different one. And so we're 95%. This is another tip for the exam. If you're asked to explain the confidence interval in context, it always starts as we are whatever percent confident the true mean or population mean difference in anxiety levels is between whatever. So this reinforces that the difference in anxiety level on this test or this instrument, it lowers it between 0.51 and negative 1.71. So it lowers it, and 0 is not in there. So that kind of reinforces that it does help on average lower anxiety levels by doing this. So just a note to self there, if you're asked to interpret the confidence interval, say we are whatever percent confident the true mean or proportion or difference in means or difference in proportion or whatever it is between that whatever interval you found. And the last one is 2 independent means. Well, before I go on, how about number 4? Questions on 4, the paired data.
Can you walk through how you did part E?
Part E?
Yeah,
so
the T.
Yeah, the average difference was lowered at what, 1.125. So that's your average difference. That's your mean difference. And then it's plus or minus, and then this is your T multiplier. It's the same way we found it in the T table, 95%, 15 degrees of freedom, same thing. And
Got
then
it.
I give you
yeah, I missed part of the problem that they had given us. Yeah, that information. Perfect. Thank you.
You bet. So like a common error here would people would put like 1.96, right? They'd use the Z multiplier. Okay, I'm just going to take 1 point off for that. Or if they'd looked one row off and said like 2 point, it's not that, it's going to make almost no difference here. I just want to make sure people know there's a difference between the T and the Z. So let me know that you know, oh, there are different distributions, there's different multipliers. I have to look at this other distribution to get these numbers. And yeah, great question. Others for number 4 here, this paired data. And like I said, that test I just graded, they wrote it out just like this, but they wouldn't even had to put the numbers in. just write that formula just in case they screwed up over here, like I did. See that? I scribbled it out twice. I hit my I must have done something wrong with my calculator. It happens, but I would still give some credit here for that. Fat fingered it. And then the last one, two independent. So these are comparing length of company A and company B electric toothbrushes. So the null hypothesis, there's no difference. The alternative is that I think the one works better, as they claim, that the B. And instead of making you do the formula or write it out, and this one I was nice and just gave you the t-score. And it was negative 4.77, which is a very large t-score, which means yes, there's a p-value is probably close to 0 at that point. And so we can reject the null and say there is significant evidence company A toothbrushes last as long as company B. So I can also do that, or I could ask you to actually do the calculation for the difference between two means, which you should be able to do with all you need is the mean and standard deviations. And I'll pull up the formula sheet for that one, just so you can see it. So that one would have been right here, two means right here. Yep, there's the two means. Our null hypothesis is that mu1 and mu2 are equal. So this is always 0. For every scenario we're using, these are always 0. But what this does is if you already had an existing known difference in populations, we could then account for it right here. A good example, the graduation rates for Des Moines Public versus Ankeny High School. We already know historically there is about a probably 25–30% difference in those graduation rates. But let's say they introduce a new program, and after 5 years they're trying to say, has it gotten better, or has it statistically gotten better? We could account for this initial difference, like in these proportions, like right here, and then analyze the difference between before and after a little bit. So we don't have any questions that we do like that. And there's no tests on your there's no questions in your test that have to do with the F distribution. You did that this last week, comparing the variance between two independent samples. And yeah, I don't think there's any, and there'll be some chi-squared tests stuff when you're doing goodness of fit. This might come in handy, but don't concern yourself primarily with that. Just worry about this means and proportions stuff. All right, there. I went through that exam. I went through that stuff. So I've kind of blasted a lot of info at you. What other questions might you have, or any other ones that you've looked at, the sample exams you want me to? But this is a pretty good representative of what you're going to be asked to do. I'll get a few checking the email because. All right. Anybody? Yeah. Oh, there's a chat there, isn't there? Okay, you're good. All right. Thanks, Alex. That's really nice. Thanks for sending along a couple of those questions through Ask My Instructor as well. So yeah, keep doing that. The last few chapters, linear regression and goodness of fit type stuff, or we also do tests for independence. Not nearly as difficult as what you're doing. Use StatCrunch obviously for both those. The only other thing you're doing this week besides finishing up those two chapters is preparing for the final project discussion, where you come up with an idea, make a very short video on your phone or whatever, post that on the discussion board. There's instructions on how to do that. So it does two things. It helps everybody kind of see what your idea is and can give feedback on it, including myself. And it gets you started on your project. But the next week, that's after this, then the finals week, getting your project done and submitted and making your video and getting feedback. And if you do it in a timely enough manner, I should be able to give you feedback so you can even modify it if you needed to, if there's some things that were wrong. So should do well on that. So that would be all we're doing that finals week is working on that. So if you're really on top of it, you probably get done, well, maybe even earlier if you've got a good idea, a good source for data, good analysis, write it up, make your video, be talking it out. You are welcome. Anybody else like a little assistance, anything, homework they're doing that they're finishing up, or are you all going to take the test right after this or later today, or? You're welcome, Sid. Thanks for being here. I will post this recording as well later. It doesn't take usually too long. I'll blast an announcement out with the link. Thank you, Ellen. Thanks for getting this lined up too. I really appreciate that. Heidi, how about you? Any questions you might have? Oh, okay, great, awesome. Do well, and usually it takes about an hour. So I had give you 2 hours, but it should be plenty of time. If you want to practice, doing one on your own before, that's even better. So you get the kind of the rhythm and the pace that you need to keep. So, all right, thanks for being here. Oh, yeah, oh, she left. Okay, pause the recording.